For this lesson, we will look at optimization. Now, optimization is basically finding the extrema, the maximum or the minimum point. Now, in the previous lesson, we have learned that we have to use the first derivative f prime to find where the function is increasing and decreasing and to find the maximum and the minimum point. And we have discussed about the local or the relative maximum and minimum. On the other hand, the second derivative, the f double prime, tells us where the function is concave up or concave down. It also tells us the point of inflection. And the point of inflection is where the graph changes concavity. Okay, taking this in and applying it to optimization. Okay, let us take a look at the following problem. Now, this time, okay, I want you to take note that we want to find the absolute, okay, the absolute maximum and the absolute minimum value in a given interval. Okay, so you can only find the absolute if you have a closed interval. So take a look at this problem. Find the absolute maximum and minimum of the function f of x equals x cubed plus 3x squared minus 9x plus 7 on the interval from -6 to 0. Okay, so we're finding the maximum and the minimum, which means that we have to find the first derivative. So we get f prime of x. And the derivative of f of x is 3x squared plus 6x minus 9. Now remember, when you get to find the maximum or the minimum, we have to set the derivative equal to 0. So we take this derivative, 3x squared plus 6x minus 9, and set it equal to 0. So in this case, we can factor out the 3 or we can divide everything by 3. Okay, and that gives us x squared minus 2x minus 3 is equal to 0. And from here, we can factor. So we have x minus 3 plus 3, x minus 1 is equal to 0. So we got two values for x here. We have -3 and +1. Now, taking a look at the interval, your interval is from -6 to 0. So -3 is within the interval, but 1 is not. So that means we can discard 1. So this is discarded because that is not within the interval. Now, if we're finding the local or relative maximum or minimum, then you can just say -3 could be the relative maximum or minimum. But here, we want to find the absolute. So in other words, when you find the absolute, you have to test including the endpoints. So here's how, this is called the candidates test. Okay, this is called the candidates test. Candidates test. Okay, meaning we have these x values right here. Okay, the endpoints, -6 and 0, and the critical value that we got here, which is -3. And then we want to find the value of the function at each of these x values. Now, whichever gives us the highest value, that's your absolute maximum, and whatever gives you the lowest value, that's the absolute minimum. So how do we find it? Okay, we have to use or to evaluate the function, the given function, this f of x here at each of the values. So f of -6 will have -6 cubed plus 3 times -6 squared minus 9 times -6 plus 7. So we'll evaluate the function at -6 and we will get -47. Then you do the same thing. You find f of -3. So you plug in -3 for x and you will get 34. Next, you plug in 0 for x. So if you plug in 0 for x, you will get 7. Okay, so from here, the absolute minimum is the lowest f of x value. So we say the absolute minimum is the point -6, -47. And the absolute maximum is the highest value for y, which occurs at 34. So the absolute maximum point is -3, +34. Okay, let's take a look at problem solving this time, application to business. So let's have this problem. A discount appliance store is selling 200 television sets monthly. If the store invests X $1,000 in advertising campaign, the ad company estimates the sales will increase to, so this is the sales, n of x is equal to 3x squared minus 0.25x to the fourth plus 200, where x is between 0 to 9. Now remember, x represents the amount invested in the advertising campaign, and n of x represents the number of television sets, okay? So determine the point of diminishing returns. Now the point of diminishing returns, this is basically the point of inflection, okay, where the concavity changes from concave up to concave down. So meaning, what does this mean? This means that we have to find the second derivative, okay? And the second derivative changes from positive to negative. Meaning, if it changes from concave up, the returns here are basically increasing more rapidly. And then here is your point of inflection, and then it changes to concave down. So here the revenue still increases, but at a much slower rate. That's why it's called diminishing returns. Okay, so for letter A, it says, determine the point of diminishing returns. We want to get the point of inflection, and therefore we have to get the second derivative. Of course, we need to find the first derivative first. So the first derivative here would be 9x squared minus x cubed. That's the first derivative. And then we get the second derivative, which is 18x minus x squared. Okay. Now we want to find where it changes concavity. So we have to set this equal to 0. So we can factor out the x, and you'll have, you can, wait, 3, this is 3x squared, sorry about that. So minus 3x squared. So we can factor out the 3x, okay? And this would be equal to 6 minus x is equal to 0. So two values for x is equal to 0, and x is equal to 6. Okay, now if you take a look, we have 2 points of inflection here. However, your lowest boundary here is equal to 0. So that means there is nothing to the left of 0. So 0 cannot be a point of inflection because we do not have any curve to the left of 0. So we don't have a change in concavity. So we can discard the 0 here, okay, and just use x equals 6. So the x value of the point of diminishing returns is equal to 6. Now letter B, show that this is the point of diminishing returns. So that means we have to show that at x equals 6, the concavity changes from concave up to concave down. So we have to use the second derivative sign chart. So here is your 6, that's the point of inflection. So you want to get the sign of the second derivative, and this is from 0 to Okay, so what we want to do is to test a point that's between 0 to 6. And let's say we get f prime of 1. Let's just say 1. So we get 3 times 1. We'll plug it in here. Multiplied by 6 minus 1, which is equal to positive 15. So here you have a positive value for the second derivative. Now next, we find or we test a point from 6 to 9. So say, for example, 7, we get 3 times 7 multiplied by 6 minus 7, and this gives us negative 21. So it's negative right here. So that means that the curve changes from concave up to concave down. And so therefore, x equals 6 is a point, the x value of the point of diminishing returns. Okay. Now, for letter C, it says how many televisions will sell at the point of diminishing returns? So meaning when x is equal to 6, what is n of x? Okay. So we have n of 6. How do we do this? We plug in 6 into our x in the n of x function. So we have 3 times 6 cubed minus 0.25 times 6 to the 4th plus 200. And this would give us 524. So 524 TV sets for at the point of diminishing returns. Okay, and this next one, I guess this is the last, second to the last example. An office supply company sells X shredders per year at P dollars per shredder. The price demand for this shredder, price demand means the price of one shredder. Okay, for X units demanded, if X units is demanded or bought, then the price would be 300 minus X over 30. So that's the price. So the question is, what price should the company charge? So we want to find the value of P for the shredders, to charge for the shredders for maximum revenue. If we want to maximize the revenue function, that means we have to find the revenue function. So the revenue function, okay, remember revenue is equal to the number of items times the price per item. So in this case, the number of items is X and the price is equal to P. The price per item is equal to P. So in other words, we just multiply P times X, the price times the number of items. So this P here will be multiplied by X. And so we get our revenue function equals to 300X. And I'll write this down as 1 over 30 times X squared. Okay, so we multiplied 300 by X and X over 30 by X. Now, since we want to maximize, it means that we have to find the derivative. The derivative is equal to 300 minus 1 over 15 times X. Since we want to maximize, we set this equal to 0 to find the critical number. And solving for X, we get X is equal to 4,500. Okay, so this is the number of shredders that needs to be sold for maximum revenue. So to answer the question, at what price? So the price would be equal to 300 minus, we plug in 4,500 into X, 4,500 divided by 30. So solving for P, the price would be equal to 150. So the price of the shredder is $150. Okay. And then you're asked to find the maximum revenue. So we have this revenue function. What is the revenue when X is 4,500? So we get R of 4,500. We plug in 4,500 for X. So we have 300 times 4,500 minus 1 over 30 times 4,500 squared. And this would give us 675,000. Okay, so that's the maximum revenue. Okay, we'll have one more. If exactly 200 people sign up for the charter flight, the fee for the flight will be 300 per person. Okay, so that's the original. Now remember, okay, if more than 200 sign up for the flight, each fare will be reduced by $1. It means that for every additional person that signs up, the fee will be reduced by $1. Okay, we want to find the number of passengers that will result in the maximum revenue. So we are maximizing the revenue for the agency. Okay, which means that we have to find the revenue function. Now remember that the revenue, okay, is the product, in this case, of the number of passengers times the cost per passenger. Okay, so originally, the number of passengers is 200. So if there are 200 passengers, okay, the cost is equal to $300 per passenger, right? Now, for each additional person that is added, so if you add X number of persons to the flight, what happens to the price? The price will be reduced by $1. So it will be reduced to minus 1x, right? $1 times the number of people. So this is your revenue function here, okay? Now, we want to maximize the revenue. So we want to find how many passengers would there be. So we need to find the derivative, okay? So, but before we find the derivative, let us FOIL this. Let us multiply this together. So multiplying this together, we get 60,000 plus 100x minus x squared. And then we get the derivative. So the derivative would be 100 minus 2x. And then again, we need to set that derivative equal to 0 and solve for the critical number. Our x here is equal to 50, meaning 50 additional passengers. Okay, so it says in the first question, how many passengers will result in the maximum revenue? Remember, this is the number of passengers, the 200 plus x, and this is the cost per passenger, right? Okay, so number of passengers would be equal to 200 plus x, which is 50. So the number of passengers would be 250. Okay, second, find the fare needed to maximize the revenue. Now the fare is this, the cost per passenger, okay? So the fare would be equal to 300 minus 50, which is also 250. So $250 per passenger, okay? And then the maximum revenue. So we have to find R of 250. No, R of 50. Okay, X is 50. So R of 50 is equal to 60,000. Oh, you know what? We can just simply multiply the number of passengers by the fare, right? So the total revenue would be equal to 250 times 250, which is equal to 62,500. So the maximum revenue is $62,500.